8, 7, 6, 5, 4, 3, 2, 1.
What's up, everybody? You're watching NASA in Silicon Valley Live for December 6th. I'm your host, Cassandra Bell, and if you didn't know, this is NASA in Silicon Valley Live, a conversational talk show out of NASA Ames Research Center with the various scientists, engineers, and researchers, and all-around cool things that you need to know about. I'm here with my co-host, Abby Tabor.
Hey, Cassandra. Hey, everybody. Welcome back. Thanks for joining us again. If you like that nerdy NASA news, we are simultaneously live on Twitch, YouTube, and Facebook. But if you want to join us in the chat and ask our guests questions, you got to join us on Twitch. So that is twitch.tv/NASA. And if you can't catch us live, no big deal. We'll have the video on demand later, including on NASA TV. And if you want to listen to the audio-only version, you can catch us on your favorite podcast service. So today, I'm very happy to introduce you to our special guests, Andrew and Jim. Can you tell us your full name and just a little bit about what you do here?
Sure. My name is Andrew Helton, and I'm a research scientist here at NASA Ames, and I study evolved stars, so stars nearing the end of their lifetimes.
Ah, interesting. Cool.
And I'm Jim DeBiser. I'm a scientist here at Ames as well. My main field of research is how stars form, and I also work on astronomical instrumentation. So these are the cameras and instruments that we put at the back end of the telescope that collects the light, that takes the image or studies the object in space that we want to observe.
Okay. That's pretty essential for astronomy, right?
Yeah. So today, we're here to talk about airborne astronomy. So can you tell us a little bit about what that means, airborne astronomy?
Yeah, so when you think about astronomy, you might think about the dome on the top of a mountain in an isolated mountain range somewhere, or you might think of a satellite in space. But one of the other places you can do astronomy is from the atmosphere, and that can be from a balloon or from a sounding rocket. But what we're going to concentrate on talking about today is astronomy from planes, so putting a telescope on a plane to observe space.
Okay.
Telescopes on planes.
That's clearly awesome, a telescope on a plane, but why would you do that? What's the advantage?
Sure. There are a number of different advantages to having a telescope on a plane. You can imagine that not all astronomical events happen at the same place on the surface of the Earth. And so sometimes you might need to take your observatory to where that event's going to occur. And of course, a plane's a mobile platform, so you can go anywhere you want.
Yeah.
And so that's one reason. Also, you have people on board. So if you have problems with your instruments during a flight, rather than being stuck in space where you can't access them, you're right there. And so you can work on it. The plane comes home every night, and so you can make changes to the instrumentation. You can make repairs as they're needed.
Right, right.
And then in addition, since you're flying on a plane, you can get up into the atmosphere where you can start to see emission that you wouldn't otherwise be able to see from the ground. You start to see wavelengths of light that are impossible to detect from a ground-based observatory.
Okay, tell us more about that. What is a wavelength of light that we're not going to see down here?
So, for example, our eyes are sensitive to optical light, so the visual portion of the spectrum, which is actually just a very small fraction of the total spectrum of light.
Like the rainbow?
Like the rainbow, yeah. The
That's
rainbow
the
is just a
visible
very,
section,
very
right?
narrow portion of all of the electromagnetic radiation spectrum. And so if you're wanting to observe in the infrared portion of the spectrum, which is a wavelength just a little bit longer than visual, you're not going to be able to see that from the ground because the atmosphere absorbs most of that.
Okay, so infrared is like remote controls, right? Like for the TV, that's how that works to change the channel.
That's right. And so your eye can't see it, right? But you clearly see that it's affecting your television, right? And that's infrared radiation, and that's what we're looking at.
That's what you're looking at.
Oh,
Awesome.
okay, light we can't see with our
Light that you
eyes.
can't see with your eyes.
Okay.
That's right.
Well, I think we have an infrared camera to see what we look like in
awesome.
infrared.
Nice. Let's
There it is.
There's Andrew and Jim. Hi, guys.
Infrared. Awesome.
And so here, this is emission from warm objects, right? And so if you're looking at this display here, anything that's dark is cool for the most part, although Jim might talk about that. Anything that is bright is warm. And the exception...
So yeah, you see my forehead and my mouth are pretty hot because they're the sort of the brighter yellow colors. My nose is cold; it's darker. My My glasses look very dark, but that's not because it's cold. It's because the infrared light can't actually go through my glasses. If I take off my glasses, you can see my eyes. They're pretty hot. But I put my glasses back on, and then the infrared light can't penetrate through that.
Okay, very cool.
Very cool.
Didn't you tell us this is like predator vision?
Yeah, that's right.
Is that true?
That's right. It's similar
Essentially.
to what Predator saw heat, and so when he was looking for his victims, he looked with heat vision.
Okay. Good to know. I have a question from the chat from Bandit CRN. Why is it important to use an infrared telescope for space exploration, and what do you hope to learn from this? So, like, why would you look at this kind of light?
Right. So, as Andrew said, the optical light that we see with our eyes are only a very small part of the entire electromagnetic spectrum. So, in order to understand what's going on in space, we want to look at other wavelengths to see what other wavelengths these objects emit at. Now, it turns out that stars, the surface of stars, give off light that we see with our eyes, and most of the things that other things that we see are because that light is reflected off those objects to us, so we can see them. But the great part about the infrared is all objects have heat, and that's what the infrared traces. And so all objects give off infrared light. In fact, a majority of the light in the universe is given off at the infrared wavelength. So it allows us to observe almost every astronomical object in space at a very interesting wavelength that we can't see with our eyes.
Okay. So you said we can see things in infrared that we can't see in visible light. So I think we have a picture of visible and infrared light to sort of
Compare
what this. Here we go.
Right, so here we have an image of the Sombrero Galaxy, and you'll notice that there's a halo of what are isolated stars, mostly isolated stars, but then around the waist of the galaxy, there are these dark lanes, and those dark lanes are lanes of gas and dust, and they're dark because they're absorbing a lot of that visual light, the portion of the rainbow spectrum that our eyes can see. They're absorbing that material. So if we go to the next
If we
image,
go into infrared,
here
same
we go.
galaxy.
Wow.
Same galaxy, but now you'll notice that what was dark in the last image is now illuminated because it's emitting the infrared light.
So
So
that
it's
pink?
absorbing the optical, but it's emitting in the infrared.
And you don't see the stars
And you
anymore.
don't see the stars as well.
Okay. So that pink is the dust glowing.
And that's the dust glowing.
Okay.
Yeah, that's right.
Very cool.
Yeah, so the other advantage about working in the infrared is it has a penetrating power. And what I mean by that is a lot of times in the center of galaxies or where stars are forming, they're surrounded by a lot of gas and dust, which makes it impossible for us to see what's going on with our eyes or with optical wavelengths. But the infrared light comes through, so we can detect that and we can see how stars are forming. So the analogy to that is firefighters, when they go into a burning building, there's a lot of smoke. They might not be able to see the people they're trying to save if they don't have goggles, which are IR goggles, which allows them to see through the smoke and see the heat signatures of the people, the bodies of the people who they're trying to save. So
Very
it's a very similar technology in what we're doing in astronomy. So
That is cool.
So that sounds like a very on-the-ground kind of use for infrared, but why would we use airplanes to do infrared astronomy?
Airplanes, as I mentioned earlier, allow us to get up higher into the atmosphere, and infrared is absorbed in our atmosphere by water vapor. And water vapor is very efficient at absorbing infrared radiation. And so in our atmosphere, it turns out that most of that water vapor is at the lower levels of the atmosphere. And if you get as high as what we call the stratosphere, it becomes very dry. And so you can now see in the infrared. It's now transparent where we're trying to observe.
Okay.
And so once it gets to the stratosphere, yeah.
Okay, so I think we have an illustration to sort of show what that is, what we mean by the stratosphere. And maybe while we're waiting, oh, here we go.
Here we go.
Yeah.
So yeah, you'll see there's two layers of the atmosphere here. There's these rays of infrared light, which are shown as red. And you see as they come down through the stratosphere and into the lower atmosphere, they start to become attenuated or drop off. And the light doesn't make it all the way to the ground. However, there's a plane there in the stratosphere where it's intercepting that infrared light. So that could be the light from an astronomical object, for instance. And so that's the reason why we try to get up there into the stratosphere.
Yeah. A bunch of people want to know, like, Resonator Games is asking how high do these telescopes fly? So what's the altitude for SOFIA right there?
Normal cruising altitude for when we're doing observations is anywhere between 39 and 43,000 feet.
Okay.
So what is that in relation to where a commercial plane would fly?
So a commercial plane flies about 35,000 feet.
Okay.
But at that height, it gets us above 99% of the Earth's water vapor in the atmosphere. So
When we're up around 40.
around 40,000 feet,
Okay.
yeah.
All right.
So
Excellent.
NASA's been putting telescopes on planes for quite a while.
Yes.
That is
And we have
true.
some models here to talk about all these telescopes on
I
planes.
do. I have an early example here. This is the Learjet, right?
Right, so this is the NASA's Learjet Observatory. So this was one of the earliest airborne observatories in the infrared. And it started flying in the late 60s. It had a telescope that was 12 inches in diameter on board. And so that's a modest-sized telescope. Yeah, it's about
Yeah.
that big in diameter, about that long. A lot of people who are amateur astronomers have telescopes of that size in their backyard, but in this case, it was one of the first infrared telescopes. So we're looking at the infrared part of the spectrum. So it did make a lot of discoveries. And if you see here in the front, the hole here, it's not really a hole, but that's the telescope sitting out or pointing out the side of the plane.
And what can you mention some discoveries made from this Learjet?
Yeah, so I think there were a lot of discoveries made because, again, it was one of the first infrared observatories. But one of the interesting ones was it totally changed how we perceived or how we thought about Venus. Okay. So prior to these observations, a little bit prior to these observations, we knew that Venus had lots of clouds in its atmosphere. We knew that it's about the size of the Earth, but it's a little bit closer to the sun. So a lot of people thought that, well, Venus is probably like this very lush tropical paradise, lots of rain, maybe even vegetation or plants and things on the surface. And just before these Learjet observations, they found that there was no water in the clouds of Venus. And the Learjet actually determined that the major aerosol constituent of the atmosphere is sulfuric acid.
Very different from
it's
water.
Very different. So now, instead of a lush tropical paradise, our picture of Venus is sort of a hellscape. It's so hot on the surface it melts lead and it rains battery acid.
Not a good vacation spot.
No.
We're not going there anytime soon.
Yeah, no. Okay. So that was a cool finding from the Learjet. Now let's fly in my second example here.
Even the next airplane.
Yeah.
Move it on up.
All
A
right.
new generation of airborne astronomy there. What's this one?
So this is a model of the Kuiper Airborne Observatory, which was the next generation after the Learjet.
Okay.
The Kuiper was a C-141 military cargo aircraft that was converted to house a telescope. Just like the Learjet, you can see that the telescope is in front of the wing right there, just behind the cabin. It's quite a bit larger than the Learjet was, right? So before the Learjet had a telescope that was only about 12 inches in diameter, so about 1 foot. This is about 36 inches, so 3 feet. It's about 3 times bigger. And the aircraft, of course, is quite a bit bigger as well. The Learjet had a passenger space for about 4 people with pilots.
Oh, really?
And then
That's
here
it.
we even have an upgrade, so you can have about 12 people on board. So it's still pretty small, but that's mostly because it's taken up, the fuselage is taken up with a lot of equipment and computers and whatnot. If this were just a passenger jet, it would be about 150 people or so on board, compared to the Learjet's, 6 to 12, something like that.
Yeah.
And I think we have a picture of what it was like inside
here we
this
go.
plane. You mentioned not having a lot of space.
All right.
Yeah, so here we go.
Yes, there it is. So you can see that most of the fuselage is taken up with computing equipment and control equipment. It looks kind of like something from an old missile silo or something.
And that's just inside our C-141. And what years did this fly for?
So it flew from about 1975 to about 1995, and it was very active during that time. So it conducted a lot of research. It flew for about 7.5 hours at a time, and it would fly 2 to 3 times a week. Again, it made a lot of discoveries similar to the Learjet. It was one of the first observatories that observed the atmosphere of Pluto, for example.
Wow, Pluto.
So yeah,
Our
Pluto.
favorite, not a planet.
Yeah, Pluto, not a planet.
Hashtag Pluto, not a planet.
That's right. And we're actually lucky today to have one of astronomy's supervillains.
That's right.
Supervillain? What did you do?
It was the 2006 International Astronomical Union meeting where they decided to reclassify Pluto from a planet to a dwarf planet. And one of the main sort of contentions or things that people think wasn't quite right about it was towards the end of the meeting and there weren't a lot of astronomers left. There was only a few hundreds of us from the couple of thousand that were there for the whole meeting.
Okay.
But we had the vote, and Pluto was determined not to be a planet. And I just want people to know that there was a majority opinion, a very large majority opinion of people who thought that Pluto should no longer be a planet. And for good
astronomers
reasons.
who
Astronomers,
agree.
yes,
Yeah.
actual astronomers, yes.
Doesn't fit the mold.
It does not fit the mold
Yeah.
of a major planet. That's correct.
It's okay to be a dwarf planet.
It's
That's
not
all
wrong with
right.
it. It's still a cool planet. It's still a cool place.
People talked about it getting demoted, but
Yeah,
it's
no.
okay.
Yeah. And what else did the Kuiper discover? Studied lots of things, you said.
Well, another one that people find very interesting is the discovery of rings around the planet Uranus
Oh,
was
really?
also done by Kuiper. So that's another popular one.
Very cool.
Very cool.
Those are some pretty big discoveries.
I know.
Yeah, they are.
That's exciting.
Yeah, that's definitely true.
Awesome. Should we move on
Yes,
to our
let's move it on
third
up.
plane? This one's
Yes.
very exciting. This is no ordinary airborne observatory.
It is the biggest, the
The world's largest.
World's
largest,
airborne
most
observatory.
modern.
And this is what you guys work on, right?
That's right.
That's right. So this is SOFIA. This is the Stratospheric Observatory for Infrared Astronomy. And this is the mission that both Andrew and I work on. And so we're now looking at a 747 that's been heavily modified so that there's a much larger telescope in the back. So in Learjet, we were talking about a 1-foot telescope in diameter. Kuiper was a 3-foot in diameter. Now we're talking almost 9 feet in diameter on this telescope here.
9 feet.
9 feet inside an
pretty huge.
airplane. That's
Yeah.
correct.
Yeah. Wow.
Yeah.
Cool.
And how often does this fly? This is, you said, the world's largest observatory.
World
airborne
largest observatory. It flies 3 to 4 times a week and 10 hours on a flight, so a little bit longer than the Kuiper, which was at 7.5 hours, and Learjet only could fly for 3 hours. So we have a lot more observations coming out of SOFIA than we did those two facilities.
Yeah, and you'll notice that here the telescope is behind the wing, whereas in the other two models it was in front of the wing.
That's true, yeah.
It makes it much easier for the pilots to access the restrooms in flight, so that's a
yes.
good thing. There's a lot more space to move around.
Okay, great.
So normally, if you're on a 747 passenger jet, it can house almost 300 people or so, and so it's a marked increase in size from the C-141 that was the Kuiper. And the telescope is in the rear, as I mentioned, and that hole, just to give you a sense of perspective, is about the size of a normal garage door, right? So that's how large a hole in the cavity.
And you said that's
is.
a hole.
That's a hole.
Totally
It's
open?
open to the atmosphere.
just
It's
open that
open
up.
to the atmosphere. It's not a window. And so if you look carefully at the fuselage, you might be able to make this out. There's a little rise leading up to the opening, and that rise was very carefully engineered and tested here at Ames, in our wind tunnels here at Ames, to take the air and direct it over the cavity and to have it redirect to the backside so that there's no turbulence in the cavity, or at least very little turbulence in the
No
cavity.
drag.
So it's very smooth airflow across that. The pilots assure us they can't tell if it's open or closed. It's almost seamless.
Oh, wow. And I think we have a video of this door opening, this
Yeah.
garage door in the back of the
I want
747.
to see that, yeah.
Yeah, so
Okay,
here's
you're fine.
SOFIA in all of its glory in flight, sunset trip. Yeah, and here's one of our test flights where we were opening the door for the first time. So you can see the door slowly opening in the back there, and eventually it'll open to about 10 feet in size because it's a 9-foot diameter telescope. So
And if you think that it looks like it's a little bit stubby for a 747, you're correct. It is. It's actually a 747 SP, so it's a special performance 747.
Okay.
They only made about 40 of those, but it's just a smaller, shorter version.
But we're on board. We're on board during these. It's not like they're being the telescope and the instruments are being remote worked.
Right.
We are on board the plane at the time. We are moving the people on board are moving the telescope. The people on board are using the instruments and collecting the data.
Oh,
It's a pretty
yeah.
active work environment.
Yeah,
on board,
Yeah. What is that like? Are you moving around? Are you fixed at your computer screens? What is it like on board?
Well, we have different stations where different people do their work. There's a station for the telescope operators who point the telescope to where we need it to go. There's a station for the instrument operators. These are the people who are looking at the data coming out of the cameras at the back end of the telescopes. There used to be eyepieces at the back of telescopes. Now everything's digital cameras or instruments
Okay.
that collect light and analyze light. And then you have mission directors who are talking between the scientists on the flight deck and the pilots up in the cockpit to organize how things in the flight are going to go. And of course, you have the pilots up top because they're on the on the second level on a 747.
And of course, there's still a lot of space on board, and so there's plenty of room for investigators who are actually the people we're conducting the observations for, the people who have proposed the research. They can come on board and see their data as it's coming in.
Oh, other astronomers?
Other astronomers from all over the world can come join.
So our crew, including visitors, are typically somewhere around 20.
Okay.
And the Kuiper could have maybe 7 people on board,
Right.
and the Learjet could only have 4 people on board besides the pilots.
I think we have a video on board Sophia showing a little bit about the environment and what it's like.
Yeah, there's our second home.
Yeah, that's right.
So yeah, what you're seeing here is that's the back of the mission director's computers that I was talking about, the mission director's stadium. That's the science station there. That's where the people who are looking at the
Is that where
data
you
come
and
in.
Andrew sit?
That's where
we sit,
that's where
yeah.
we would be. We were watching and analyzing the data come in on the astronomical instruments.
And if you're paying attention, people were facing the telescope, and so your back is to the direction that you're flying, right? You're facing
you're sitting
backwards.
So you're saying opposite of what you would
That's
in a
right.
commercial airliner.
Okay.
That's right.
Okay. That's
Okay.
funny.
And is that so everyone's facing the telescope?
We can watch and monitor what the telescope is doing.
Okay.
That's
right.
Cool. I have an important question from Venom Plays 777. Are there in-flight meals?
There are not in-flight meals.
Oh,
There's no
no.
catering except what you bring on board yourself.
Oh,
we
man.
do
Bring your
have
own.
we do have a galley which has microwave ovens. We have a coffee maker. We have refrigerators.
Now, for years we didn't, and there was a lot of
Yeah.
celebration when we finally got a coffee maker.
Yes,
Yeah.
yeah,
That
and the
Nice.
microwave. That's great.
Yeah.
All right. BYO snacks.
Yes.
That's right. Bring your own snacks. 10 hours, so you need a lot of
Oh,
food.
yeah.
That's right.
Oh, yeah.
That is true.
Oh my gosh, you get exactly what you want then.
Yeah.
Right?
Yeah, lunch is at midnight, so you have to taste things
Okay. That's great.
Because you're flying all night.
all night long. Yeah.
Okay.
Yeah, cool.
But I mean, we could actually observe infrared in the daytime as well, but we use optical cameras to find where we are in the sky, and so that's why we have to observe at night.
Makes
All right.
sense.
I'm getting a lot of questions. How about we move on to
Yes.
our first segment, rapid fire questions. You
Rapid
ready?
fire. All right.
Ready?
All right, you asked for it, so here we go again. Rapid fire questions is where we cover as many questions from the chat as we can. So let's go. Quick questions, quick answers, and we'll hit as many as we can. There was a good question. Well, first of all, what's the observing cadence for SOFIA from Core Accretion?
So we typically observe 3 to 4 nights a week, and then that will occur on over a span of 2 to 3 weeks. And then we'll do an instrument swap, put a new instrument on, and do the same thing again. And that happens pretty much year-round.
Cool. Okay. Space TV Net is asking, is the SOFIA telescope design more similar to a space telescope or a ground telescope?
Yeah, it's much more like a space-based telescope. We actually point and maintain our pointing through gyros, so just the way a space observatory works. And so, yeah, when you're in flight, there's turbulence, the telescope looks like it's bouncing around. It's not actually bouncing around, it's actually stabilized, inertially stabilized with respect to the stars. So that means it's not moving. Everything you're seeing is us bouncing around the telescope. So it's much more like a space-based telescope.
If you're not careful, it can give you a sense of seasickness just trying to watch it, because it moves around a lot.
Yeah.
Yeah.
I think we're going to see some of that later. That's pretty cool. Why use a plane? Are there advantages as opposed to common satellites? Could you review that a little bit for 8-Bit Pepper?
Right. So I mentioned easy access, which is a really big one. You know, if you launch a satellite and something goes wrong, either you're out of luck and it's just a lost mission, or it's a very expensive process to go about fixing it.
Okay,
Right. It takes
right.
a dedicated mission to fix it. Here we don't have that problem. Since we come home every night, we can address any issues that might arise. So that's one of the big advantages of being on board a plane as opposed to a satellite.
The other one is we can upgrade the technology. When you plan for a satellite mission, by the time you actually launch the mission, it's a couple decade-old technology.
Right.
Since we come home every night, we can put the latest technology on board and try things out, and maybe even be a pathfinder for technologies that are used on future satellites.
Oh, yeah.
We've had a number of upgrades just over the last few years.
That's correct.
Yeah, that's right.
cool.
Yeah.
Awesome. Bag of Spaghetti is commenting, that is pretty cool. And Fergus Digmus says, this is an incredible piece of engineering. And it is, and
is,
just
yep.
you wait. There's more to come. Why a bay door instead of a window from Resonator Games?
Yeah, so
question.
there's 2 reasons. One, since we're looking in the infrared, we are looking at heat, as we were talking about. We want the telescope as cool as possible. So at the higher altitudes that we're flying, we can get, minus 30 degrees Celsius, so it gets very, very cold. And we want our telescope to be cold because that gives us less background emission from the telescope. So that's one reason why we kind of want to open. It's sort of passively cooled by the atmosphere. But the other reason is there's very few materials that we can make a large window of this size out of that allows us to look at all of the wavelengths of infrared light that we're interested in looking at. Like I said, my glasses earlier are made out of material that block infrared light at the wavelength at that camera. So our cameras look at a very broad range of wavelengths, and there just isn't material available in this size that would be able
a garage door size sheet of diamond.
Of diamond. That would work.
Well,
That would
you don't
work.
That sounds heavy.
You don't have that?
And
Expensive
difficult
as
to
well.
make.
All right. So many good ones. Are cosmic ray strikes an issue for SOFIA data? Core accretion.
For much of our data, it's really not. And even for our optical cameras, where it is more of a problem, if you're taking a lot of images sequentially, then it's easy to remove cosmic ray hits. Okay. So most of the time, it's not an issue. Even for our optical cameras, we can deal with that if we need to.
Yeah, our detectors aren't as sensitive to cosmic ray hits, and because we co-add data, we take very short exposures and co-add them, it gets averaged out. Any cosmic rays get averaged out.
Okay. What's the distance that SOFIA can see in terms of light years, basically, from David Espel?
Well, that's a tough one because it depends on how bright something is. So we did recently observe a quasar or something like that that was at
It was a lens galaxy.
That was at a very high Z is 6 or something like that, maybe even more.
What's that
I don't
mean?
even remember. So what that means is it's very close to the dawn of the universe. So in terms of light years, again, it's all dependent on how bright the object is.
Okay, so it's more about
In
brightness.
that case,
It's more about brightness.
we were able to do it just because there was something in front of it that acted as a magnifying glass.
As a lens.
Okay.
And so that's why we were able to observe that.
Okay.
Interesting.
Maybe this is related. Solar Captain's asking, is SOFIA going to be able to see further away than the observatory telescopes? I think ground-based observatories, I suppose.
Yeah, again, it all has to do with the brightness of the targets that you're looking at. Yeah. So we can see things very far away as long as they're bright.
And mostly that's a function of the size of the telescope. So the bigger you go, the easier it is to see faint objects, which may be farther away. Right?
Yeah, and most of the wavelengths that SOFIA works at, we are now the largest observatory that there is. So there is the most light collecting power that we can get out of any facility is with our large telescopes.
Right, and there really is very little way to upgrade the size on an aircraft, right? Because the fuselage of a 747 is about as big as it gets. You can go a little bit larger, but it's not going to actually increase the size of your telescope very much.
We can't get a bigger telescope on board.
You just can't squeeze in anything else.
All these upgrades from the early airborne observatories to now, the bigger plane was to get the bigger telescope.
That's right.
That's right.
Okay.
That's right.
Yep.
Okay. Maybe one more, because I've got a bunch of questions that are going to come up in the next section.
Yes.
So we're going to hold on to those. Let me see. Is the data recorded during these missions available to citizen astronomers from Fourth and
That's a
Inches?
good question. So yeah, we do archive all of the data that we have. Most of our data is from people who have proposed to use our facility and have gone through a selection process. They have a proprietary year to look at it and do what they want with the data. But then after that, the data is public. You can go to our data website and download it. You just have to register your email. And that's it. So anybody could use it.
We do also have a number of what we call director's time programs, and those are data that we observe and then make it immediately available to the world. So anybody can look at that data right now. In fact, just a few days after it's been observed.
Oh, cool.
Cool. These are great questions.
Yeah, and there are lots more. But
We'll get to those later.
Yep.
So this is a reminder that you're watching NASA in Silicon Valley Live. And today we're talking about SOFIA and airborne astronomy. Have questions? Put it in the chat. And we will get to them when we can. But we love your questions.
Yep. We're saying goodbye
Bye to Jim and Andrew. Thank you for joining us. And now we will shortly have with us our guests, Kim and Ken, Kimberly, ENNICO, and Ken Bowers. Welcome. Thank you both for joining us. Let you get settled here.
Yep.
Yes. So
Please be here.
all tucked in.
Yes.
All good.
Welcome, Kim and Ken.
It's a tongue twister.
Okay.
Yes. You could tell us a little bit about what you do here and introduce yourselves.
My name is Ken Bauer, and I'm an engineer here at NASA Ames. And my job is easy to explain, but hard to do.
Okay.
I
plan missions for SOFIA, the airborne observatory.
Very good.
And I'm Kimberly Ennico Smith. I'm a research astrophysicist here at NASA Ames. And as an astrophysicist, I'm studying the phenomena of the universe. And I also do a lot of design and evaluate missions to study the universe.
Oh, okay. So a lot of people are using SOFIA to do a lot of different science. Can you give us a little taste of what kinds of things you observe and study?
Absolutely. As Jim and Andrew were talking you through this amazing, the world's largest flying observatory, we have astronomers from all over the world applying for time to study the infrared universe. And a lot of their science is all about our origins. You know, how did we get here? Science about what are the conditions under which stars can form, the stellar nurseries. How do planets form? How do atoms, ions, molecules in the universe get into planetary systems? And we study a variety of objects from nearby, like comets and asteroids and planets in our own solar system, to star formation regions all over our own galaxy, the Milky Way. There are a variety of shapes and sizes.
It's amazing how many astronomers want to study dust.
Dust.
Dust, a very big thing.
Dust is where, you know, a large fraction of the light in the universe is irradiation with dust.
Wow.
We also study other galaxies outside of our own Milky Way, even some of these lens galaxies that Andrew had talked about.
Okay.
Cool.
Yeah.
So we talked a little bit about all these cool things that SOFIA is looking at, but how you talked about planning these missions.
Yep.
So that goes into how we do that. Can you explain about that for us?
Sure. It starts more than a year before we fly a mission, and that's when we ask people, what do you want to look at? So scientists all over the world propose observations that they want to make. And then we take all of those, and there's about 5 times as many proposed observations as we could possibly observe. We put those in front of a panel of esteemed scientists, and they rank them for merit. And the list comes to me, and I only get the top 5th, and the names are taken off. And my job is to try to schedule all of those observations. Okay. It's a complicated jigsaw puzzle because the Earth goes around the sun, and you see different stars at different nights, and the Earth is spinning as well, so the stars are rising and setting. And if you look at the airplane, you'll notice that the telescope is always on the left side of the airplane. So that means that if I want to look at a star in the north, I'm going to fly the plane to the east. If I want to eventually come home, which we'd like to do, so we can fly the next night, I need to find a star in the south to observe at the right time of the night. So it's a big jigsaw puzzle, and the pieces change every time you put one down.
Wow.
Because the Earth rotates and all the stars are now in a different location. We'll be tuning our flight plans from 10 weeks before we start flying, a particular clump of them.
Okay.
And we'll even be adjusting it the day of.
Wow.
Because most airplanes do care about wind, but not that much, because you just want to get someplace in an airplane.
Right.
So where the plane is going is fine. If there's a crosswind, you just lean into it a little bit, and you'll get there a moment later, and it doesn't really matter. We can't do that. We have to point the plane so that the telescope is always looking in the right direction. And if the wind needs to blow us, it's going to blow us. So part of the job of a flight planner is to adapt to the wind and make a flight plan that will work, given all of those conditions.
And sometimes we bring the plane down to the southern hemisphere. Astronomers want to look at the southern targets in the southern hemisphere as well.
I see.
So the plane moves to a different airport and does flight operations out of there, and still doing the flight plan, still the same geometries. You know.
So you
many
mentioned
pieces.
changing from hemispheres, but if you're flying from the same base night after night, it's the same flight plan every night?
So it is never the same flight plan.
Okay.
Even if we wanted it to be, it's never the same flight plan because the winds change a little bit. And even if you just say, I'll fly last night's flight plan over tonight, well, the Earth has gone a little ways around the sun. And so
Things have shifted about 15 minutes.
It's constantly changing.
Yep.
Yeah.
So
That's crazy.
So-
Okay,
A lot.
so we're talking a lot about the plane moving all the time, all these factors affecting it. I mean, the wind is blowing it, the stars are moving. I've been on a plane. I know there are times when I can't even stand up because the plane is shaking so much. And there are a bunch of questions here from Resonator Games, Grupfeld, Core Accretion, Gamez76. Everybody wants to know, how do you stabilize the telescope? So let's go to our next segment, Explain It Like I'm 5. All right, so grab your sippy cups, folks. Explain It Like I'm 5 is when we ask our NASA guests to explain a complex scientific concept and make it understandable for us kindergartners. So take it away, Ken. Explain how you keep the telescope stable, and focused on a target.
It's one of our most common questions. If you've ever tried to look at Saturn with binoculars, you know that the thing bounces all over the place, and it's you that's moving. You don't have to move much for something that's that far away to be very difficult to see. So you want your telescope to be very stable. And that's great when you're talking about a building on a mountaintop, but it's not so great when you're talking about an aircraft. You've been in aircrafts, most of you have been in them, you know that they move. And aircrafts tend to rock and roll a little bit as they steer around, and they tend to go through vibration. There's an engine hum all
Kimberly's
the
doing the
time.
vibrations worth.
Yeah, it's a toy model there.
This is a model of the telescope, a bit larger scale. That's back
right
there.
here. Yeah.
And it is mounted inside what's called a spherical bearing. It's like a ball and socket joint, like your shoulder is.
Yeah.
So there's one sphere and type of another, and that allows it to rotate freely in 3 different axes. A little bit this way, and a lot this way. While the telescope is flying, it will be making changes because as the Earth rotates, the stars appear to rise and set, and so the telescope will be tracking along. And if it gets out of range, the plane just moves a little bit.
We actually use the plane to do some of the steering in this direction of the
To point the telescope.
To point the telescope.
And when the plane goes through some turbulence, the telescope can adapt to it. And we can often watch this. When I've been on the flight, I can watch this telescope bouncing up and down, in fact.
It moves that much.
Yes.
You see it bouncing around?
Yeah, it moves quite a lot. It'll go up and down a couple of feet.
So how does that
sometimes.
affect the image quality?
The astounding thing is that it does not affect the image quality. I can be watching this thing go up and down, and this is moving up and down a foot or two at a time. Quite within a second or two, it can go that far. And yet I look out the image that the camera's looking at, and it's a completely still image. It could have been a photograph, a still shot.
Wow. I think we have a time-lapse video showing what it's like on a flight.
Awesome. Let's see.
So this is sped up, I think, 50 times. And as much as it looks jittery, seeing it moving around all over the place, this is actually a pretty stable flight as they go. I don't see really big motions. When you see it make a big rotation, like that is changing its target. And the little motions you're seeing are all the corrections for what the plane is doing. In addition to these corrections, to sort of cancel out the hum, the whole thing is sitting on a giant air cushion. So it's sitting inside a ring of inner tubes, and there are other fancier devices that help cancel out those high-frequency hums.
Interesting.
Yeah, and the science instrument is shown in the center there with the bags of white, which are the when the cryogens on board are changing to vapor, and so that is just taking the spectra of the target, and there's an electronics rack over to the right, and the telescope structure is that blue structure. It's moving quite rapidly in the sped up version.
All right.
And when you're on board, I mean, you can feel the plane moving, and you're seeing on the screen, and the image is rock steady. You just know the telescope is compensated. Some amazing German engineering. The partner on our SOFIA project is the German Aerospace Center, and they delivered us one awesome telescope.
Okay,
Yes.
sweet.
Yeah. The short answer to your question is we have really good tools.
So
That's awesome though.
Sambone100 wants to know, does the telescope have adaptive optics?
So does it have adaptive optics? A bit. There are some devices on the back, and the secondary can do some motion. It's kind of a technical answer, so I won't get into too deep questions.
And we don't have, we're not using classical adaptive optics like ground-based telescopes where they use a sodium guide star or anything like that. We don't do any of that, that activity.
Most of our adaptive is about canceling vibration.
That's right.
And His Majesty wants to know, does it adjust by itself or some software?
Well, I don't think it's ever going to take care of itself. There are gyroscopes, and there's software in the loop, so the gyroscopes remember what way up is and keep track of make all the corrections for us. But it's all software in the loop, yes.
Okay.
And we also have the visual centroiding with the images on the star itself. We have 3 guide cameras of large field of view, medium field, and fine field of view, and you're constantly tracking multiple stars. So you can take out rotations and stay on point.
The gyroscopes can try to keep you pointed in the same direction, but the same. You don't want to be pointed in the same direction. You want to follow the star as the star moves.
Right.
Okay.
Everything's always moving. I have a message for Trooper Nix. We're live. Have a question for our guests. Write it in the chat. So I want to get that out there. Gosh, there are so many questions.
Kira would like to know, what does it mean that you typically fly north-south?
So typically, if you've looked at some of our flight paths,
I think they heard you say if you want to look south, you have to fly a different direction.
So the airplane flies towards its nose, but the telescope only looks out the left side of the aircraft. So if I am flying north, then the telescope will be looking to the west. So I'm looking at some target, some star that is setting in the west. And if I'm flying south, and the telescope is looking to the east, so I'm looking at something that's rising in the east, and those have to be balanced out. We need to end up flying the exact same amount of time north as south, as east, as west.
So Ken's often trying to find targets that the astronomers want, but those that are rising and those that are setting.
Yes, okay.
It turns out that in the south is a lot more things that astronomers want to look at in the north. So I spend a lot of time trying to balance.
It's where the action of the
South
universe
versus
is.
north. Yes, it is where the action is.
Okay.
Nathan Maya, I think, is asking if Sophia ever looks back at the Earth in infrared. You'd have to fly at an angle facing the camera to the Earth, so we realize that would be
very simple
complex,
answer, no.
No.
Designed to look up.
We can only actually look, not even at the horizon, only 20 degrees above the horizon, up to 60 degrees above the horizon. And if we were to bank the telescope like that, I think all the passengers would be very uncomfortable.
Yeah, you'd have to change the plane.
Well, we have so many great questions live, but we are going to run out of time if we don't move on to talk a little bit about some of the objects that Sophia studies.
And that's what people want to know about as well.
Yes. So, Kimberly, I've flown on a few flights with you.
Okay.
Get these models out of the way. Yes. And on a couple of the flights I've been on with you, we've been looking at black holes. So can you tell us a little bit about Sophia's black hole observations?
Black holes, one of many different type of targets at Sophia. So black hole is an object whose gravity is so strong that not even light can escape. And there's actually quite a few black holes in our Milky Way, but they're hard to find.
Oh, yeah.
They're hard to find the signatures. In fact, they're 1 out of every 1,000 stars may eventually go through a black hole phase in our Milky Way.
Okay.
You can sort of get a sense of it's very massive. Just imagine our sun, but 10 times the mass of our sun concentrated in an area like New York City is what a stellar size black hole would be.
Wow.
There's even bigger ones out there. They're called supermassive black holes, and these are the ones that have millions or billions of solar masses. And the center of our Milky Way has a supermassive black hole.
It's our galaxy.
That's Milky Way is our galaxy, and the galactic
a lot
center.
of astronomers want to look at that.
It's like I've planned so many flights.
And
at
it's
this
in the south.
And also there are lots of galaxies outside the Milky Way that the astronomers call them the term active galaxies. And it's because if you were to add up all the light from the stars, they're brighter than what the stars themselves would give off. And they're also emitting at all different wavelengths: X-ray, gamma rays, radio, infrared, visible.
These are types of light
all the different types of wavelengths. And a lot of telescopes are looking at this. And then we, with these active galaxies, Sophia's been looking at a few of them. And
like which ones?
We recently looked at Cygnus A, which is 600. It's one of the brightest radio galaxies. It was discovered originally in the radio. It's about 600 million light years away, and it is understood to have a supermassive black hole that's about 2 billion solar masses.
Oh,
2 billion suns.
2 billion suns. So if our
Supermassive.
galaxy has 4 million, this one's got about 2 billion. Super massive.
And it's eating very actively now.
Yeah, because what the understanding is, why is it so bright? It's because all the material may be falling into the black hole and emitting at all these different wavelengths. So there's a model to explain what a black hole, an active galaxy with a supermassive black hole looks like. And it has this dusty ring, which is the material for which is feeding that central part of the black hole.
I think we have an illustration of what
you brought a
Cygnus A
picture
black hole
straight
might
over.
look
Cygnus
like.
A, here's an artist representation of Cygnus A, and what's striking about it is it's got these dusty ring, you sort of see as this grayish material, and these jets that are emitting from the center, perpendicular, right angles to the ring. And if your clever eye is looking at it, you can see sort of looks like tinsel, since we're in the Christmas season. Tinsel surrounding the ring.
Oh, all around that dusty.
Yeah. And that is a representation of magnetic fields. So SOFIA made observations of the orientation of magnetic fields around Cygnus A.
Oh, wow.
And one hypothesis is it confining the dust and therefore providing unlimited food supply for this supermassive black hole?
Awesome.
Also, the magnetic fields could be some way to channel the energy, like warping space and time and turning it into a coil, and then being the source of those relativistic jets coming out.
Like
So
a
SOFIA is
spring,
going to be
right?
studying a lot more of these galaxies, with and without jets, to see whether what's the strength of their magnetic field.
Looking for magnetic fields.
That's exciting.
Very cool. So black holes are one of my favorite things, but I know you want to talk about some of your favorite things. Can you tell us about some other things that SOFIA studies? What might be one of your particular favorites?
What's your fave, Ken?
I'll tell you about one of the big challenges that I have in planning is an event called an occultation. An occultation is the general case of an eclipse. So if you've seen a solar eclipse or a lunar eclipse, it's only called an eclipse if the Earth, the Sun, and the Moon line up together. If it's three other objects, like a star and a planet and your eye, that's called an occultation. So it's a general case. And if you participated in last year's eclipse across America, hopefully somebody, got to see the complete eclipse. I did not, because it did not happen here in California. It went all the way across the country and missed us. And sometimes you have to be where the action is. And the shadow of the moon is just a small spot compared to the Earth, so we didn't get to see it here. By most observations that I make, it's just a question of saying, is the star up? Can I point at it? But in the case of an occultation, I have to be at exactly the right spot on the Earth to observe it as well.
Like in the path of totality.
Yep, in the path of totality.
And the size of the totality, the size of the shadow is equivalent to the size of the object you're looking at. So a bigger object will cast a bigger shadow, and a smaller object will have a smaller shadow.
So we look. The biggest object we've looked at is Pluto. And,
or hashtag not a planet.
Not a planet, yes.
I think we have an animation
I was gonna
to sort of
say,
show what an occultation might look like.
So we're flying along. You can see the planet, and it's just now moving in front of a bright star. There it goes, and the shadow is now cast upon the Earth. SOFIA is flying through the shadow, and there's a bright flash. So that was the moment where the star and the planet and the shadow on the Earth were all exactly lined up. And we want to try to hit that central flash, it's called. And that can be really tricky to try to hit, even given the shadow size of Pluto, about the size of Australia. The central flash goes by really quickly.
So you said it's about the size of Australia. How long do you have to study that? When what we saw in the
about a little
animation?
less than 2 minutes, about 1 minute and a half, 90 seconds.
90 seconds.
90 seconds.
Oh my
Yes.
gosh, better not miss it.
All the
And
science
you have
need
to
to
be within
do.
about 50 miles or you'll miss the central flash
Wow.
entirely. And we like to try to be within 5 miles. And we're moving at 500 or 600 miles per hour at the same time.
And the shadow's moving about 50 or 60,000 miles per hour.
Oh my gosh.
So we're definitely not shadow chasers. We are.
Shadow interceptors.
Yes.
Okay.
You need to be there when it gets there.
Yes.
Yeah.
Yes.
And
Wow.
what do you
Otherwise you miss
learn
your
when you study objects like this? What did you learn about Pluto?
Well, you can learn about its size, because when you cross the shadow, you get the size of the object. You can also learn about its atmosphere, depending upon how the light curve changed, this dimming in the light. And you can also learn about the environment. Uranus, its rings were discovered by the Kuiper Airborne Observatory
right. We talked
through an
about that.
occultation measurement, because it was an unexpected result. And again, they found rings around a body. So occultations say about its size, information about the atmosphere, and whether there's rings or other satellites around the object.
Amazingly, Pluto, for being so far and cold, has also got a dynamic atmosphere. It's changing over time.
And that has been confirmed by many occultations over the several decades
awesome.
since its discovery.
SOFIA found that out first.
Yeah.
That's awesome.
Very cool.
Yeah, cool.
So you talked about searching for rings and for areas around this. What other objects have you looked at, search for rings for with SOFIA?
So summer of 2017, we studied a Kuiper Belt object called 2014 MU69.
And for the audience reference, I think we have an illustration of what the Kuiper Belt is.
Yeah.
So
run us through
Kuiper
that.
Belt's this region in the solar system out beyond the orbit of Neptune.
Yeah. Do we have that image of the Kuiper Belt, Dave?
It's not to be
There we
confused
go.
with the asteroid belt, right?
Yeah, so this is a region in the solar system beyond the orbit of Neptune, and Pluto is a frequent visitor of after its 250-year orbit, the king of the Kuiper Belt.
It's the most famous one, yes.
And a billion miles beyond Pluto is MU-69, or 2014 MU-69, a very small rocky body.
Okay.
And what was Sophia looking for?
So we were an opportunity presented itself, and this is an object discovered by Hubble, but we didn't know anything about its size. So we wanted to catch the occultation. It's a small object. It's anticipated like Pluto was going to be like a 90-second event. This one was going to be less than 2 seconds.
Less than 2 seconds.
Less than 2 seconds.
It could even be 1 second.
You can do something with that time?
Yes.
That's crazy.
So the shadow of Pluto crossing the Earth was like the size of Australia, or the size of western U.S. from, say, the Mississippi to the Pacific. The size of this 20, 50-mile type object would be the size of Dallas, the city of Dallas,
Oh, wow.
Texas. So
All
a
right.
tiny
Yeah.
shadow. And we're still at these same speeds. We're traveling this fast, and the shadow's still traveling that
Okay.
super fast.
So you
It's
had to
going by
walk.
50,000 miles an hour. Don't blink.
Yes.
No.
Yeah.
It goes
we had
by
a-
very
we had a-
quickly.
So we had a very fast camera on board, just like the same frame rate you get at a movie theater, 20 frames per second.
Okay.
For something that take 1 or 2 seconds, it would take several measurements, like 10 or 15 images.
Okay. Get as
And so
many
we
as you
went-
could in that second and a half.
And the event happened, and we actually caught a bit of it, of the occultation, in 2 of our frames.
Wonderful.
Yeah. And we were also interested in the environment around it. Do these objects have rings or other satellites?
Oh,
Because
okay.
when you get that small, the calculations predict that you're in these swarms of different types of lots of bodies.
So there could have been debris
Lots of
and
little
a lot of
whatnot around
debris,
it.
yeah.
Okay.
Very-
Okay.
Can you tell us a bit about why we were searching for debris? What other mission was interested in that?
That was NASA New Horizons mission. NASA New
What's
Horizons flew by Pluto.
We have an animation of New
okay.
Horizons going past Pluto. Dave, can you roll that?
There you go.
There it is.
Grand piano-size nuclear-powered spacecraft flying by Pluto, and there's an artist representation of Pluto. The flyby was in July of 2015, and in the distance there is Pluto's moon, Saturn. And so it was Sharon, and there is a flyby of Pluto there, and the spacecraft is continuing to exit the solar system, is taking lots of pictures of Pluto and Sharon, and when it wasn't slowing down, and so
Moving really fast.
and yeah, it's on an escape trajectory, and its next target is 2014 MU-69.
Okay.
So
Sophia
our
looked at.
occultation with measurement with Sophia was to look for the environment to help inform the flight planners, because this is a year and a half out from their flyby. Flyby is in January 1st, 2019.
It's coming up.
This
New
is New
Year's
Year's
weeks.
Day.
Yeah.
So we helped the flight planner teams for New Horizons, get an early glimpse of the environment around their next target.
All right.
We
Make
determined
sure.
it's pretty clean, so
It's
they
clean.
can get close.
Yeah.
Okay.
If
Up
it had
close
been
and
very
personal.
dusty and chunky, they'd have had to stay far away.
Well, that'll be exciting to watch New Horizons fly by. So if you want to ring in the new year with NASA New Horizons and learn all about this piano-sized spacecraft, visit nasa.gov/New Horizons.
Yeah, and as a quick reminder for everybody watching, this is NASA and Silicon Valley Live, and today we're talking about the world's largest airborne observatory, SOFIA. We're going to have time for another round of questions, so leave your questions in the chat, and we'll try to get as many as we can. You guys up for a few more questions?
Bring 'em on.
All right. Cassandra, do you want to switch back and forth so we can hit a
Sure.
bunch?
I see Sneaky Rhino 1 wants to know, how long does SOFIA stay in the air, and does it refuel?
How long does it stay in the air? Typically, it's a 10-hour mission. So from wheels up to wheels down is about 10 hours. And that's a pretty long flight. If I were flying it as a passenger, I'd be uncomfortable. But I get to get up and walk around. It does get cold and it does get loud on board. Without all sorts of passengers and seats all over the place, the rumble of the plane is pretty loud. So we actually wear hearing protection most of the time that we're there. Does it refuel? So in-flight refueling? No, it does not. We land the plane and refuel it.
But astronomers would love that, because there's always more targets to look at.
But our crew does want to go home with their family.
Longer flights might be nice, but the reality is we only observe at night. And so even if we were to try to do a 20-hour flight, we don't have 20 hours at
Well,
night.
late breaking news is that at certain wavelengths, we can be observing at longer wavelengths.
Yes.
Oh, okay. Yeah.
But we need to refuel.
Yeah.
Does the plane have to fly without lights to not interfere with the telescope? I suppose? And does this cause issues with flight laws? Nailfile1 asks.
So that's not an issue.
Okay.
We turn off the lights that are shining on the telescope itself. But other than that, we turn them off. So the logo light, that's the light on the plane that shines on the plane itself. We
On the
turn those
tail?
off as well. Yeah.
Yeah. Okay.
Oh, okay.
But the blinking lights, the red and the green,
They're on
they're on the whole time.
Because you're following all FAA rules, and they're emitting in the visible. And as you remember, our telescope looks in the infrared.
Exactly,
and
right.
So, and it doesn't interfere at all with our cameras, our guide cameras that work in the visible.
Cool.
Yep. So we do follow all the FAA rules. And that is a big deal for flight planning.
I bet.
Anti-Particle 73 wants to know, are there multiple SOFIA in operation?
Nope. Just one.
And Space VNet would like to know, who was the genius that first had the idea of an airborne observatory?
Oh, I don't know the answer to that.
Yeah, I mean, there was earlier we learned about the Learjet in the 1960s, but even prior to that, there was a smaller jet that was put up, and they just stuck a camera outside the window and just to see what you can measure, because you knew about this property that the atmosphere was blocking the infrared. And when the first infrared detectors were being made, they took it up and they realized that we are missing a lot of the universe up there.
The answer is the cool people at NASA.
Yeah, so.
Nice.
That sounds like it. They've been
Curious
doing that for a long time.
Could SOFIA be used to observe a comet and its tail?
Absolutely.
Oh, yeah.
And it has.
Oh, yeah?
Yeah, several times. We have one coming up.
Yeah. Comet Vertinen?
Vertinen, yes.
Vertinen, yes. So that's going to make its perihelion around December 16th or so.
That,
Yep.
what does that mean?
Yeah.
Oh, closest to the sun.
Okay.
So when a comet gets closer to the sun, it gets more active, and you can see a lot more of its activities. And so in the infrared, we can study the gas and also the dust and the ice. So we can look at water, we can look at carbon dioxide, we can look at methane, we can look at any of the constituents, and also the temperature. So we do a lot of comet studies.
Okay,
Yep.
neat.
Yeah, whenever a comet comes around, it gets scheduled. We even have open observations. If a comet were to be discovered, it would get bumped up in the queue to be observed.
Okay. Fred Burkhoff is asking, what is space made out of? That seems like a simple question, but that's actually...
Oh, that's a
Really?
cosmological question.
that's
You can
tough.
say,
That's a good question.
we often use the term gas and dust.
Yeah, I
So
thought
what is gas? Gas is
told me that.
atoms. They are molecules when you have more than one atom. You have ions, which are when you remove an electron or a neutron and you charge it. And then dust is solid particles. And some astronomers like to call dust anything that's heavier than helium. So sometimes carbon, oxygen, and nitrogen, if there's a lot of it, is a solid. We call it dust.
Considered a dust. Okay.
Planets are giant aggregates of dust.
Yeah.
Right, right.
But yeah, what is space made out of? And then there's the gap between the gas and the dust too.
All right,
Good
we won't get
question.
into dark
Good answer.
matter today.
Yeah, there's that topic for another day.
So maybe you can tell us a little bit about, in our last minute or so, what SOFIA is looking at going forward. You mentioned this comet, maybe what they're looking at this week.
This week, I can tell you what we're looking at tonight.
Oh, tonight.
So we're taking off in about 2 hours' time.
Cool.
So 6:40 p.m. on Pacific time, 9:40 Eastern, 2:40 in the morning if you're at Greenwich Mean Time. And it'll be flying about for 10 hours, and we'll fly out of Southern California, fly up to Manitoba, then across to Vancouver, and back down to Southern California.
All the way up to Canada and back south.
Yep.
Okay.
And then in that time, we will observe 3 different stars at various stages of their life. We're going to look at one that has a newborn inside of a cloud. We're going to look at a toddling, spewing planet and an aging, lost its hair already bald planet. And finally, at a great view of M51, a galaxy that's like the Milky Way, but close enough we can get details, and it's face on.
And you can use your favorite flight tracking program, and our tail sign is the NASA 747.
Oh, cool.
Yeah,
So type
so
it in
watch
tonight.
us in 2 hours.
Yeah.
SOFIA, okay.
Awesome.
Well, thank you both for joining us. We're just about out of time. So thank you for watching and for all your questions in the chat. This has been NASA in Silicon Valley Live, a conversational talk show out of NASA Ames Research Center with the various scientists, engineers, and researchers, and all around cool people, where we talk about all the nerdy NASA news you need to know about. If you like that, we're simultaneously live on Twitch, YouTube, and Facebook, and NASA TV as well. And if you can't catch us live, don't worry. We will be video on demand after the fact, and you can also catch us on the podcast services on the audio version. So a huge thanks again to our guests.
Yes,
Yeah,
thank
you're very
you.
welcome.
Thank you.
Glad to
Thank
be
you
here.
both.
And thanks for the questions online.
Yeah.
Right,
Very
exactly.
good.
Thank you to everybody in the chat who joined us. And we'll be back on Thursday, December 20th for a special holiday unboxing episode. So be sure to join us for that. And until then, thank you for watching. Bye.
Bye.